Hello everyone, good afternoon and welcome to today's Yebo physics session. So for today we'll look at a topic on conservation of energy and a few questions from your TAT practice quiz, which is from TAT 4. There's just a few questions to look at there. I'm sure you have gone past the conservation of energy, so this should be a simple one. And for those that would have missed a few of our live sessions, this is the opportunity to recap and see if there are any concepts that you still can grasp. So without wasting much time, we'll go look at the question number 11 of TAT 4, which is showing on the screen. And this question relates a 3 kg mass, which is dropped from the edge of a 50-meter tall building with an initial speed of 0. And the mass strikes the ground with a downward velocity of 25 meters per second. Find the change in mechanical energy of the mass caused by air resistance between the point where it is dropped and the point where it strikes the ground. So if you look at this question now, you are just dealing basically with the conservation of energy, and your initial energy there is present in the 3 kg mass as kinetic energy. Sorry, as potential energy, which is stored energy by virtue of the position of that mass above the ground. So because it's on a 50-meter tall building, the potential energy, we'll call it EP, is given by the product of mass times the gravitational acceleration times this height. So to evaluate that, this is 3 kg multiplied by 9.8 and multiplied by the height h, which is 50, and all units are in SI units. So with that, this should give us a potential energy of how much? What potential energy should we get for that part? If I'm getting 1470 joules for the potential energy, then with this energy, the mass begins to fall as it is dropped. So initially it doesn't have any kinetic energy, but as it begins to fall, its kinetic energy increases until it has a kinetic energy at the time of contact with the ground. And at that point, the kinetic energy EK is equal to half the mass times the square of the velocity, which is the impact velocity, and that's 0.5 times the same mass, which is 3.0, times 25 meters per second squared. And that product there should give you something like 937.5 joules. Okay, so that's the kinetic energy with which it hits the ground. So you would expect, if the energy is conserved, you'd expect all the potential energy to have been converted to kinetic energy at that point. But no, it doesn't. Why is that? And how does that help us with this question? How does that help us with this question? So the difference is a result of the loss in energy due to the mechanical energy that works against air resistance. So now the question is, find the change in mechanical energy of the mass caused by this air resistance between the point where it is dropped and the point where it strikes the ground. So this change in mechanical energy is a result of the air resistance, which is the difference between the two. So delta E will be equal to our EP, or the final anyway, E final minus E initial. So E final is the EK on impact, E initial is the potential energy EP, which gives us 937.5 or 0.9375 kilojoules minus 1.470 kilojoules. So this change in mechanical energy should be a negative because it's a decrease. So that gives us negative 0.9375. Sorry, not so that's 1470 minus that, it's actually negative 0.5325 kilojoules. Negative 0.5325 kilojoules. So this is the amount of energy lost, and hence it's negative. The change is a negative because the energy is lost from this system due to the air resistance. So we have that 0.53 negative on B, and that can be confirmed. Like that. Okay. So that's a result of conservation of energy. So you see that the mechanical energy of the system there is relating the kinetic energy and the potential energy, and also the other forces that are present in the system resulting in the loss in mechanical energy, which is the change that we've just calculated. Now, the next part, champion athlete can produce 1 horsepower, which is 746 watts, for a short period of time. If a 70 kg athlete were to cycle to the summit of a 500-meter high mountain while expending power at this rate, she would reach the summit in how many seconds? So that's an interesting question there. So we are told 1 horsepower, 1 HP given here is equal to 746 watts. What do we understand by 746 watts? It's 746 joules every second. That's the first thing you get from the units given there. Now we have an athlete, mass 70 kgs, and taking this mass upwards to the summit of a 500-meter high mountain while expending power at this rate. So how much time will they take to reach the summit? So in other words, we have by the time we get to the summit, our potential energy will be the mass times the gravity times the height, which will give us 70 times 9.8 multiplied by 500 meters. So this gives us the energy to get to the top. Which is 343,000 joules. So now a simple question. How much time would it take for this athlete to expend this amount of energy? So that's asking the same question in a different way. We found that the amount of energy they would need to get to the top of the mountain will be 343 kilojoules. And if they are using 746 joules every second, then how much time will it take to spend 343 kilojoules? So knowing that power, like we did that conversion from watts to joules per second, power is equal to delta E over time. So what we want this time is time, which is delta E over the power. And the energy expanded is 343,000, and the power, which is the rate, is the 746 joules per second. So it gives us the time in seconds. What is that time? So I'm getting 459.8 seconds. 459.8 seconds, which is in seconds there to two significant figures. That would be 460. That would be 460 seconds. So we have 460 seconds on B. Which is fine. So that leads us to the next question with the spring system. A spring with stiffness 600 Newton per meter is placed in a vertical position with the lower end supported by a horizontal surface. A 2 kg block that is initially 0.4 meters above the upper end of the spring is dropped from rest onto the spring. What is the kinetic energy of the block at the instant it has fallen 0.5 meters? That is compressing the spring 0.10 meters. What will be the kinetic energy? So how do we deal with this one? How do we deal with this one? So the block, 2 kgs, is 0.4 meters above the spring. Okay, so that's our spring there. And when the block is dropped, it will compress the spring for 0.1 meters. And we need to find the kinetic energy of the block at that instant, because that is the instant when it will have fallen a total of 0.5 meters. So the spring K is the spring constant. We are given that this is 600 newtons per meter. And we know that the restoration force on the spring F is equal to Kx. So what do we do with that information? What do we need to do? So since we're dealing with energies, this is the force that will definitely oppose the spring over the distance given, and the energy associated with this spring force, it's a restoring force, we'll call it ES, is equal to half kx squared. So that means we can calculate the kinetic energy at the point of contact between the block and the spring first. That kinetic energy is therefore decreased in this case as a function of this spring restoration force, or the energy that is transferred to the spring over that distance. So what is the kinetic energy at the point of contact? Is given by basically, if we ignore a resistance, our kinetic energy EK is equal to the potential energy EP, right? What are we told about this spring? So we only know that the difference between the change in EK and the change in EP actually, so that the change in EP over 0.4 meters is that kinetic energy that we gain from initially at rest, right? So it says it's dropped from rest. If you read between the lines there, it's dropped from rest. So we're starting from that point where EK is zero, kinetic energy is zero. So to get our kinetic energy without the need to do the equations, that gives us the velocity. We can just use the mass times the g times that delta H for the change in kinetic energy, which is 2 kgs multiplied by 9.8 and then multiplied by 40 centimeters, which is 0.4 meters as given. That's in meters. So that will give us a kinetic energy of how much? 7.84 joules. So this is the kinetic energy of the block at the time when it moves or when it gets into contact with the spring. But now, at the point of contact, we still have the kinetic energy converted from the potential energy by virtue of that. So the 0.1 should be included there. So I think that potential energy should be calculated for 0.5 meters. I think the potential energy should be calculated for 0.5 meters so that we subtract the potential energy that would otherwise be at 0.5 meters minus the one that is stored within the spring over that 0.1 meters. Or otherwise add the one for 0.4 to the potential energy that is stored in the spring. Yeah, those two methods should work the same. So let's do it either way. Let's see. Anyway, I've got a guest with me. You are gonna do the other way. So what you do is you work 0.5 meters potential energy and subtract the half K squared.
Okay.
Yeah, good. Then I'm gonna do the other method. We've already got this 0.4 meters here, the potential energy or the kinetic energy through 0.4 meters. But then this, in this case, I'm gonna add the half kx squared because it is the, should I add? It is the kinetic energy. Will that be the kinetic energy? Does it add? I think. Okay, let's see. Let's see what happens here. If we have delta H, mgh, so we have our half kx squared, the restoration or the stored energy in the spring energy is half the k, we're told is 600 newtons per meter, times x squared, which is 0.1 meters squared. So that should give us 0.5 times 600 times 0.1 squared. So this is giving us 3 Newton meters, which is 3 joules. Okay. So that's 3 joules there. 3 Newton meters or 3 joules. So the 3 joules is the spring energy. And now while it's moving like that, we have okay. So while it's moving like that, the 3 joules is while it's opposing, we still have that 0.1 meters opposing that 3 joules, because we still have a force of gravity acting on the block and still pulling the gravity down. That's why I wanted the 0.1 meters to be part of this to make it simple. But we've got an additional kinetic energy, EK, which opposes this restoration force as mg, m times g, times that small distance there, which is the h during the restoration. So it still comes back to 2 times 9.8 times 0.1, and that gives us 1.96 joules. So now the total kinetic energy, EK total, will be 7.84 plus 1.96 minus the opposing or the stored energy, the one from the spring, the restoring energy. So that gives us a total of 6.8. So that's 7.84 plus 1.96 minus 3. 6.8 joules be our kinetic energy. What did you get?
I'm confused.
So what you're supposed to do is multiply to m times g. Your h is 0.5. Your h is 0.5 because remember, you have a kinetic energy that is changing from the potential energy up to that point.
Okay.
Right?
Yeah.
So which means your overall distance there is 0.5, which will be the kinetic energy you would get without the spring opposing.
Okay.
But the loss then is that difference in energy over that distance is converted into the energy stored in the spring during compression.
Okay. So we calculate the kinetic energy of the box as it travels as 0.5, right?
Yes.
And subtract that potential energy of the spring,
right,
0.1, which is opposing the motion.
Yes.
Oh, okay.
Yes. So it should give us 6.8, because anyway, that's the same thing that I did here in a way. I first calculated the one for going through 0.4.
Okay.
Then I calculated the energy stored in the spring over the 0.1. But while it is moving, 0.1 is still adding kinetic energy due to the gravitational potential, because it is losing gravitational potential over 0.1 again.
Okay.
So while that 0.1 is being opposed, but it's also there's a component of gravity that's a change in potential over 0.1 from the point above the spring to the point when it is pressed down. Because remember, that force is a result of gravity pulling it downwards. Okay. So it's still pulling it downwards while the spring is opposing. So that component adds to the 0.5. The kinetic energy there should still be the same at that point, less only what the spring is giving. That's why it was simpler to consider 0.5 once off and then subtract.
That's subtract 0.1. Okay.
Yeah. So let's see if the 6.8 is correct, because multiple choice can always give you nice answers. So where is that? Why did it disappear? 6.8, yes. So it's 6.8. So either way, it's a matter of understanding what's happening there. Remember, when we just calculate kinetic energy through 0.4, we still are gaining kinetic energy as we go down 0.1 meters. We still should be gaining due to gravity. But at the same time, we're losing due to the spring. So to just do it once, you'd rather have 0.5 in your kinetic energy, potential energy relationship. Then you consider the spring. It is the only thing that has been included in that system. Okay. So now this one doesn't have diagrams. Cubical blocks of mass M slide and side L. So it's L by L by L are piled up in a vertical column. The total gravitational potential energy of a column of 3 blocks is, okay, that's an interesting one. I'm gonna draw this diagram for you. So you have surface, then you pile up your boxes. Box number 1, L by L. So it's a cube by L again. So that's a cube. So you've got 3 cubes. So number 2 will be there, and number 3 will be there. So that's L. That's L. And that's L. So if we have arrangement like this, each is of, I think, mass M, cubes of mass M. So the mass there, number 1, number 2, number 3. So each of mass M. The total gravitational potential energy of a column of these 3 blocks will be what? So we usually assume that we've got a center of gravity which acts from the center of each block, like that. And in this case, this first center of gravity is should be at a distance of half L above the surface. The next one should be 1.5 L above the surface. Because that will be the whole block and a half. The other one will be 2.5 L above the surface. Those are the heights of the centers of gravity of each block. So now what do we do with the total? EP total should be equal to half m g times the first height, which is half L, right? So the half mg will be constant for everything, plus half mg times L2 is 1.5 L, plus the other one is 5/2 L. So if we are to find that total potential energy, then it's the potential energy of each block. And if we can add them like that, then the 8, that's 9/2 half mg times 9/2, like that. Anything close to that, we can't see the other fractions there. But then that is 9/4 mgl. That's 9/4 mgl. So we've just added or identified the center of mass, yeah, of each block and its height. So that gives us the potential energy of each block. The first one being mg times the height of the center of mass, there being half L. The other height is will be 1.5 L, which is 3/2. And you multiply that by half mg. Why did I put a half there? It's actually mgh, right? So it remains as it's just mgh. So it remains as 3/2. So it's mg, h is just half L there. The other h is 3/2 L. The other h is 5/2 L. So the half is from half mv squared anyway. So we're not dealing with kinetic energy here. So our fraction there is 9/2 mgl for the total. And it should be between A and C, otherwise I don't know. I'll just pick any of the two. It will give us and show us what the answer is. It should tell us the correct answer is that apparently I'm correct, but I can't even see what is correct there. So I thought it will pick. But that should be, it means 3 mgl is wrong, 6 mgl is wrong, 9 mgl is wrong. So that actually comes with a fraction. And so it should be 9/2 mgl or 4.5 mgl for the 3 blocks. Anyway, it's a total. It's not even an average. It's just a total gravitational potential energy of the column of 3 blocks. So we're adding the total of just the sum of each block. Okay, then the last part, two masses MA and MB, with MB being twice MA, are released at the same time and allowed to fall straight down. Neglecting a resistance, when we compare their kinetic energy after they've fallen for equal times, we find that qualitatively, what's your reasoning through that question? You've got two masses. One is MA, the other one MB, but MB is twice the mass of MA. They are released at the same time, allowed to fall straight down, and air resistance is not an issue. And how will the kinetic energies compare if they've fallen equal times? So with this question, you need to think carefully. They are coming from the same height, released at the same time, and allowed to fall straight down. And when we compare the kinetic energy after they've fallen for equal times, what can we say about that? What does equal times really imply? So if you look at potential, remember we're looking at conservation of energy. If it's potential energy of MB is twice the potential energy of MA. That's undeniable. And when they drop or fall for equal times, do they fall equal distances? It's equal distances for the two different masses.
Yeah, I feel like it.
I like that. Okay. Any reasoning behind that?
It's because like what from what I know, right?
Mm-hmm.
Like it all comes back to projectile motion. It doesn't matter the mass, like the mass of the object, they'll always hit the ground at the same time.
Mm-hmm.
So that means they'll travel the same distance.
That's true. So if you have heard of this example before, if you take a bag of cement, 50 kg is usually its mass, and a feather, and place them in a place where there is no air, in a vacuum,
Yeah.
they should fall at the same time.
Yeah. And hit the ground at the same time.
Hit the ground at the same time. So it's equal distances. So when that happens, that means the velocity should be the same for both of them.
Velocity is equal.
Yeah, because you said in this case, for projectile, you usually see that there is an independence to the mass.
Yeah.
When you're doing your motion in 2D there, that's basically kinematics, and we're not looking at the forces acting on the object. We're just looking at any object going through that system.
Yeah.
So if it's dynamics, it's different. We're gonna be looking at forces. But for in this case, then because there is no air resistance, which removes the consideration of the dynamics in the presence of those forces that would act differently on the two different masses. We therefore should expect the two masses to move equal distances through equal times, and hence they cover and gain the same velocity. So the half mv squared on a block A, or let me say the change in, okay, the change is actually related to mgh, right? So the change is not dependent on h for potential energy, but on m, right? Meaning a change will be mg delta h.
Okay.
So since the m is already less for body mb, the mgh is already less for body mb than for body ma.
Okay.
Is it so? No, body mb is greater, right?
Body mb is greater.
Body mb is greater. So body mb has got greater potential energy initially than body ma, which is half. I think I wrote half here. Ma is half mb. Then when they drop equal distances, the change there is also greater for body mb.
Yeah.
Right?
We're calculating.
Okay, so initially it's changing potential energy. The whole idea is the velocities are the same. So also for kinetic energy, the difference in kinetic energy is because of the different masses and not different velocities.
Okay, yeah.
So we ignore the velocities again because it's because of mass, and that kinetic energy for the one that has greater mass is still greater than the other by 2. The factor will not change.
Yeah.
Okay. So which one is greater by 2? KB is 2 times KA. Otherwise, KB should be 2 times KA. If that analysis is correct. Let's see. KB and KA on B. Yeah, just like that. So the velocities here are not an issue because of that condition where the bodies are gaining the same velocity over the same time, because they're moving equal distances in equal time, so it's a gaining of the same velocity. But then the kinetic energy will be different because it's also a function of mass. The two masses are different.
Yeah.
Okay, beautiful. So that's about it with this unit. I'm sure you guys, if there was anything amiss from there, you gained something. Um, we'll let you know again in the immediate future when we'll be streaming. But anyway, enjoy your long weekend. And yeah, hoping to see you again next week. It's bye bye for now. Okay.